Good morning, good afternoon, good evening, all, depending on which time zone you have joined the conference. Welcome to the session with title Multi-Scenario Power Integrity with Elastic Compute Machine Learning. My name is Konstantinos, or Kostas for convenience, and I am an implementation engineer at ARM. So what this session is all about. So let's have a quick overview on the agenda of the session. So we will talk about the sign-off challenge we came across at our latest tapeout, how we overcame that with the elastic compute benefit and the multi-scenario approach, and we will conclude with the machine learning integration section, our proof of concept, and what to take from this session as well as future work. So let's start with the same old story of Moore's law. Although it's debatable these days if it still applies, the purpose of this reference is to highlight the sign-off challenges that arise along with Moore's law diagram. So as we can see on the left-hand side, we have the Moore's law diagram, and on the right-hand side, we have some outcomes of that. So as the designs accommodate more transistors and the technology node becomes smaller and smaller, the complexity of the design is increasing. Also, the EDA vendors and their tools have to adopt and adapt to those changes by offering features that supports them and by increasing the design processing capabilities, as well as optimize the runtime, RAM, and CPU resources used to analyze the design behavior. Moving onwards, so we'll have a look on our test case for this presentation. So our test case is Neoverse N1 test chip that was fabricated last year at TSMC7 technology node. So a quick overview of the design as shown in the slide is, so how big was that? So the size was 35 million instances. We used two power domains, one which was always on and one for the two CPU clusters. So the power, voltage, and temperature conditions to analyze were the FFG typical max at 125 Celsius with 1.05 voltage for the vCPU domain and 0.825 voltage for the VDD domain. For standard cell modeling, we use the CCS, TN, and Apache Power libraries. For memory modeling, we use the GDS2RH models and AVM models that are Redhook specific. So what about the clock frequency? So the clock domains, we have some clock domains. For the CPU was up to 3 gigahertz, and for the rest of the design was varied from 1.5 to 2.4 gigahertz. And last but not least, so we have the what activity we used for the analysis. So we used the hybrid vectorless based analysis. So what that means? So it means that for the CPU domains, we used vector based approach by using the max power and the dry stone vectors, and vectorless for the rest of the design. So let's have a look on the sign-off tapeout challenge we met on that tapeout using Redhook DMP. So in order to have a full flat static IR and power EM, power integrity analysis, the tool had to run for 20 hours and 11 minutes, as you can see on the slide. And the resources used for master job were 20 slots and 22 gigabytes of RAM, while for the client jobs were 20 times 2 slots and peak memory of 383 gigabytes of RAM. So unfortunately, we were never able to run signal EM and dynamic IR full flat analysis, as the tool came across with high memory requirements, were like more than 500 gigabyte, which utterly lead to segmentation fault of the rule. So valid question at this point would be why we proceeded with tapeout if the analysis, so the signal EM and the dynamic IR analysis were failing. So the answer is that all the hierarchical blocks of the design had run standalone power integrity and power analysis, and the top level ran as well with the hierarchical blocks as black boxes. So that type of approach and analysis gave us a good boost at our level of confidence that the final post-fabricated product would have no power issues. So all that said, it was time for a change that would be able to perform the analysis that was failing. So ANSYS, in particular, came up with a restructuring of their Redhook DMP and transformed that to Redhook SC. SC stands for the Seascape platform. So what's the advantage of that new version of that tool? So major change is the elastic compute data management along with data analytics, Python integration, and machine learning as well. So what we wanted as ARM engineers from a new shiny presented tool. Eventually, we wanted some boxes to be ticked in order to start using that and deploy that into our sign-off analysis. So these boxes consist from accuracy, features, debuggability, ease of use, and UI, and capacity, scalability, and runtime as well. So what we did after an evaluation process of the tool, we came to the outcome that Redhook SC ticks all the boxes and nowadays is widely used among ARM groups at the moment as a reliable and robust sign of power analysis and power integrity tool. So that leads us to the ultimate comparison of Redhook DMP and Redhook SC, which was eventually part of the evaluation we did. So what to take out from this slide is the ability to run signal EM and dynamic IR analysis with Redhook SC opposed to Redhook DMP, as we mentioned before, with as low as 80 gigabyte peak of memory and distribution of 104 slots, which translates to 104 CPUs in total. So the dynamic IR in particular, which is the most demanding type of analysis, as it uses vectors and timing window files over timing of running simulation of the design, took 16 hours and 25 minutes, and that's less than the static IR and power EM analysis for Redhook DMP. Furthermore, a huge runtime cut for static IR and power EM from 20 hours and 11 minutes to 3 hours and 52 minutes, which if we combine with the signal EM analysis on Redhook SC, it can come up to around 8 hours of total runtime for Redhook SC. So in 8 hours, we could have static IR, power EM, and signal EM analysis all at once. So moving onwards, on the traditional sign-off approach, the analysis performed is in one scenario, but was that enough, or is this enough? You may wonder. So as you might know from your experience, the combinations of scenarios can be hundreds or thousands. Let's say like a simple approach. Simple approach is like they consist from library files which have power, voltage, temperature variation, along with the associated APL and AVM files, which are Redhook specific ones, spec files, which are the extracted wire network for all corner variations, and the Redhook tech file, which indicates the layers used and their behavior. So if we skip that long descriptive way, a good image to keep from this slide is the Rubik's Cube. So all the potential combinations of all the corners can be represented, let's say, as a Rubik's Cube. By merging the capabilities of Redhook SC on handling multiple scenarios and big data extraction capabilities. So here you can see a sample of code snippets used to handle the multiple scenario analysis and the heat map extraction for IR for the ongoing analysis that we will analyze onwards on this presentation. The runtime varied depending on the design size. So as the analysis ran on multiple designs as a test case, so it was from 1 hour to 6 hours per scenario. And the outcome of a single scenario output can be seen on the image at the right-hand side. So what we got from integrating the red hook SC and these two code snippets is essentially the heat map that you can see, and that's the IR drop heat map, and we can regulate on what we consider as worst drop and move onwards from that. So this was essentially the first goal that we had to take as an output to proceed with the further analysis. So if we take all this and move one step further, we come up with the machine learning integration. So the approach here that we will use is as follows. So the current status is that we are gathering historical data collateral with heatmap collateral exported with the designs with different corner settings. So what we've asked is from co-workers at ARM that run signoff power analysis and power integrity. We gave them these two small code snippets in order to extract these heat maps, and that will become a huge database for the machine learning deployment. So a rough number will be like 20 to 30,000 of heat maps. So we need like lots of data at this point to build a reliable historical data pool, let's say, in order to analyze things. So what the steps after that will be? So the steps after gathering the historical data is to use the pre-trained model, which pre-trained model will consist of this historical data. On top of that, we need to have around 30 heat maps, which is a rough number. So 30 heat map combination of the technology node that we work on, which breaks down to roughly 10 designs or 10 blocks, let's say, if we work on a big chip with 3 corners each. So let's say one slow, one fast, one typical, for example. So all this will be our trained model. Next step will be, so the final analysis has to be 3 scenarios of the design that we want to predict its behavior. So let's say we have a big chip as new version 1 we had. So we need to run this multiple analysis and extract the heat maps for 3 scenarios. Let's say again, slow, combination, typical, and fast one. So all this combined will give us the predictions on which corners combinations should be considered for further analysis. Essentially, make the amount of corners the engineer has to analyze from hundreds to tens, or actually cut a significant amount of number of corners that the engineer has to analyze and to dive into in order to perform this analysis. So our proof of concept. So putting that all together, we can extract multiple heat maps of different corner variations. So the approach that we followed is that we put together a user-defined parsing technique based on image recognition that proves the concept and validates our intuition that and what we are expecting to see on so-called good and bad corners. That corner combination that we used sum up to 216 in total, but could definitely become even in thousands magnitude if we consider more corner variations and more parameters on these variations. So let's say that simple, in quotes, approach that we took of 216 combination consists of so 3 temperature conditions. So we had minus 40, 85, and 125 degrees Celsius, 3 library combinations, 1 fast, 1 slow, 1 typical, and 24 parasitic file combinations, so 24 spec files, essentially. So what was the outcome of combining the heat map collateral with the image recognition algorithm? Are to cut down the number of critical to analyze corners from 216 to 54. So the IR drop target we used was 2%. So if you remember, the operating voltage was 0.8 to 5 for the always on domain, then 2% is a drop of 0.8085. So that number came out from our past experience. So that so we have we know actually from our past experience that it limits a design to operate as we expected. If that drop becomes lower than 2%, so if we have a drop like 4 or 5%, the design won't behave normally, or it might burn because the technology node is really small and all the wires became thinner, so that has an effect. So bigger drop has bigger effect on the design and its performance, of course. So we will sweep all the corners from the best one that we considered as being the slow library -40 degrees Celsius C-worst extraction. So C-worst is a type of spef extraction, to the worst one, which we considered as fast library, 125 degrees Celsius, and RC best parasitic spef file, and highlight the IR drop map differences. So we chose five corners to analyze and draw our results. I mean, we could use like more corners, so we have like more buckets, let's say. So essentially what we did is we divided the variation into buckets, and we draw the result from the best to the worst case analysis. So first one, so in the first image, this one, you can see the RC worst -40 Celsius slow library. On this one, you can see the RC worst, so the C worst, I'm sorry, slow library at -40 as well. So you kind of start seeing that the whole design drop from like, so blue, let's say blue indicates that the drop is good, and as it becomes greener and more orange and more red, it becomes that the drop becomes higher. So you can already see that some blue regions before became a bit more green now. So this one is a bit worse, as you can see. So it becomes like the blue areas become more green, the green more greener, some green areas start to become like orange. So this is the typical 85 Celsius with typical extraction corner. Moving onwards, the fast library with 125 Celsius and typical extraction. So you see some parts of the design already start becoming like really deep orange or slight red. Sorry. And the last one is the fast library, 125 Celsius and RC best extraction, which you can see it's some areas are like really deep red, which means that these areas of the design have a drop bigger than the 2% that we wanted. And what we did afterwards, so after applying a mask and the image recognition algorithm, we came to the outcome that 54 corners out of the 216 seem to have an IR drop issue, and the engineer has to analyze them further. So how we came up with this 54. So we divided the 216 as we talked with these buckets. So as we can see, the really red areas become on the top, let's say, bucket. So the orange circle on the diagram, and on the top one, so that bucket, let's say, contains 54 cases to analyze or to dive more into, and to get some further conclusions. So that will be extremely helpful for a not that experienced engineer rather than a really experienced engineer, because pretty much that's the expected results that an experienced engineer should come across. But for an engineer that does not have that much experience, let's say he has like 3, 4, 5 years of experience, he might not be familiar of which corners he should analyze, and instead of blindly start doing things, he could apply this technique in order to narrow down his corner of analysis. So with all that said, let's move on to conclusions. So what to take out from this presentation? So the purpose of this proof of concept consists from three parts. So first of all is the automation part. Automation part is the multiple scenario and the overall scripting. So as we mentioned before, Red Hook SC introduced Python. So from an engineering point of view, we had to rewrite all the process, all the reporting, the multiple scenario, all the extraction of the heat map of the GUI, everything from scratch. So and automate that, of course, because we want for the various designs. So let's say we have on my team a design, and another team has another design. So we had to automate the part that Red Hook will use the associate libraries and corners extracted for the particular design, and not mix things up or miss some, let's say, libraries or some models that are essential for the analysis. So how to make sure that all these come together and work and work by the end of the day. So to proceed with the analysis. So second point is the capability of Red Hook SC. So we found out that Red Hook SC is capable of using minimal resources to perform analysis. By minimal resources, I mean like low memory usage, so RAM. It has a huge runtime boost, and the CPU resource as well. On top of that, so Red Hook SC supports the multiple scenario analysis on big scale designs as Neoverse 1, as we saw in this test case. And last point for the capabilities of Red Hook SC is the correlation with Red Hook DMP on smaller scale designs. So how we're sure that that was actually part of the evaluation process of how we were sure that Red Hook DMP and Red Hook SC correlate. So we had a smaller block test case, and we deployed that on all the type of analysis, and we concluded that they produce the same numbers, so we get confidence on that. And last point is on what we did on this session is that we did the image recognition algorithm, as we mentioned, that proves that Red Hook SC is aligned with the expected results on the eye of an experienced engineer. So what's next? First of all, the final integration of machine learning capabilities based on our ongoing build database. So that's something hopefully we will be able to demonstrate next year on, hopefully again on 5 nanometer design or something. So secondly, the silicon and tool correlation in order to build an optimal machine learning prediction algorithm trained to predict with better accuracy the results on technology nodes like 5 nanometer and below. So what's the purpose here? So after we build all this machine learning data pool, let's say, and we build the machine learning algorithm on top of that, we will be able to predict what will be the drop behavior of the corner combinations that we will have for technology nodes like 5, 3 nanometer, 7, and going downwards, or even 7 as well. So technologies that we might not be that familiar with, as not that many fabricated products have came out of these technologies. So third is the continuous evaluation of the future tool versions to prove that it still owns the position of a reliable sign-off tool. So what we want here, I mean, we know as engineers that tool versions might have some bugs. So I mean, we won't, of course, use a version that will come immediately. We have to again test it and validate that that version is good with all the potential new features or new runtime, memory, CPU optimization resources that it might bring with it. So last but not least, and by coming to the end, closer to that of that presentation, I would like to quote one of the three fundamental values at ARM. That's win or die. So that means essentially that good results come out of good collaboration work. So on that point, I would like to thank Sean Hang, who is my co-presenter. I would like to thank you guys for your help, for the opportunity given to present this, and for the guidance as well to put all this together and make a good result.
Sorry, could you, sorry to interrupt.
Sorry?
Could you go back to the beginning of that slide? Your audio dropped for a few seconds there.
From which one? Sorry, the last one.
The current slide. Pretty much as soon as you started this, your audio cut out. So if you could just take a moment and then restart what you were saying at the beginning of this slide.
Of the
takeout.
Of the slide 28, you mean? Okay.
Yeah.
Okay. Good. So should I start now or?
Yeah, whenever you're ready.
Okay, cool. So yeah, 5, 4, 3, 2, 1. So coming to the end of this session, last but not least, I would like to quote one of the three fundamental values here at ARM, win or die. So which means that good results come out of good collaboration. So I would like on this point to thank Sean Hank, who's a co-worker of mine. He's a principal implementation engineer here at ARM. Mark Swinen, who is from ANSYS, and Anand Ganesan, my co-presenter. I would like to thank you guys for your help, the opportunity of that you gave me to present this, and the guidance as well that you gave me to put all this together and present on this conference. So I assume that's all from me. So thank you all for your attention, for your attendance, and I assume we can move on to the Q&A session.